Hi, this is Yuhao Han, and this is my SP3 transmitter physical design report. So let me introduce my design flow first. The first step is create WAV and setup environment files, including setup.yaml and source.yaml. And the second step is synthesis, including syngeneric, synmap, and synopt. The third step is floor planning, and including create floor plan shape, place I/O pins, connect global nets, and power grid. The last step is place and route, including pre-CTS, CTS, post-CTS, route, and post-route. So let's talk about the first step, create WAV environment and set up environment files. And the first step, the important step of create WAV environment is to set design name the same as top module name, because WAV needs this name to read some files and also generate some files. And in terms of the threshold voltage, I chose the RVT because it's just a regular choice. And the second thing I did is to add inject tie-load file into the inputs, because the file makes several pins tied down to ground. And the third step is that change the content in the SP3 transmitter digital source.yaml file, because WAV need the content in this file to read HDL files, so we need to change it. And the last step we need to make is that we need to change setup.SP3 transmitter digital.template.yaml, and we need to change three things in this file. The first thing is we need to add a comment that makers can inject our tie-load.tcl files into the whole flow. The post run means that after the implementation.cts.add-tie-offs, after this step, the flow tool will run the inject tie-load.tcl file. And the second thing we need to change is that decap cells, because we use RVT and the default decap cells is LVT, so we need to change that. And the third thing is that we need to comment the post-CTS uncertainty. This clock uncertainty means we have a stricter setup time violation calculation and also hold time violation calculation. But this uncertainty is too large for our design, because it is 62.5 nanoseconds. But some clock of our design, the clock period of them is just about 2.5 nanoseconds, so it's absolutely too large for our design. And after setup, let's move to synthesis. So synthesis contains three steps. The first step, syngeneric, means Janus transfer always block and non-block statements into some flip-flops, and these is just a definition of hardware. It's not linked to any library, and it's just a generic definition. And in the synmap step, Janus transfer the generic definition into library standard cells. And in the last step, synopt, Janus just simply optimize the design. And the below picture is synthesis short summary. We can see that the worst negative slack of the three steps are all positive, which means after synthesis we are currently mid timing, and the leakage power is low, and the area after synopt is 34,425 micrometers. So in the next page we will have the detailed report of that. So here we have a detailed report of power and we can see that leakage power just accounts for 0.06% total power, so it's quite low, and the internal power accounts for about 53% of the total power, and the switching power accounts for about 47% total power. And in terms of the area, the cell area is we talk about in the last page, and the net area is about 12,000 micrometers. And we will see what's the difference between synthesis area and post-route area report in the last few pages of the slide. So the left picture shows that the schematic view after synthesis. Okay, and after power and area, and we need to talk about timing and also the performance. We can see that we can see the clock period here, and for the clock 40M clock, we can see it has 25 nanoseconds period, so it's much lower than 62.5 nanoseconds, which is the default clock uncertainty in the setup.yaml file. So that's the reason that we need to comment that, because that's too large for our design. So after synthesis, we need to do floor planning. The very first step of floor planning is to create floor plan shape. And in this step, we need to set 4 variables. So the first is margin horizontal, and the second is margin vertical. At first, I set them both to 3 micrometers, but actually it does not meet requirements, because we need to add power rings, and the power rings has a width of 5 micrometers and spacing of 2 micrometers and offset to core of 2 micrometers. So obviously we need at least 15 micrometers to meet the requirement. So I changed the margin horizontal and the margin vertical into 15 micrometers. And the third and fourth variables we need to set is the die width and die height. At first, I set them both to 330 micrometers, but actually I use this floor plan, go through all the steps from pre-CTS to post-route, but at last I found that it just has about 40% density. It's much lower than 60% density, which is the requirement of our design. So I calculate that the 248 micrometers will just meet the requirement, and it's the largest floor plan I can make, which meet our requirements. So I set the die width and die height to 248 micrometers, and it shows that we have 72.5% density just after floor plan. Oh, and by the way, I find a comment that name the check floor plan report density. Using this command, we can see our density just after create a floor plan, so we don't need to go through all the procedures. It can save a lot of time. Okay, the next step is to place I/O pins. So we are required to place input pins on the left and place output pins on the right. So I just write the comment in left, and the 4 means the fourth layer, and 1 means the spacing distance. So after that, we need to connect global nets. Global nets is used to connect something. Maybe there will be an analog micro in the future. So we need to use global nets to connect our core with the analog macros. And after we connect global nets, we can see VDD and VSS in the Innova GUI. And the first step is to create follow pins and power grid. So we create follow pins first because follow pins are always on the bottom, and and we create in the horizontal direction. And then we create power rings, just as we mentioned in the first step. They are used to ensure the power of the core. And the next step, we create the power stripe on the M5 layer. So we are required to create power stripes from M5 to M9. So here is M5 to M1. And so the comment shows that the top layer is M5, the bottom layer is M1, and direction is vertical because we need to make the adjacent layers or the adjacent power grids in the different directions. So the follow pins is in the horizontal direction, so we made the power stripes on M5 into the vertical directions. And next step is just similar to the last step. We just change M5 to M6 and M1 to M5, and also direction to horizontal. So we create power stripes on M6, and also we create power stripes on M7. There's something we should notice, that is we double the stripe width and set-to-set distance every one vertical and one horizontal layer, which means we create M5 power stripes and M6 power stripes. So M5 is vertical, M6 is horizontal, is a set, and after this set, we need to make M7, the power stripe on M7, their width double and double their set-to-set distance. So we use this comments, set stripe width double and set-to-set distance also double. And from the left picture, we can see that the yellow power stripe is power stripes on M6, and the I don't know its color, the red or something power stripe is on M7, and the M7 power stripe has a 3.6 micrometer width, and the power stripe on M6 just has 1.8 here, 1.8 micrometer width. So which means we double the width of them. And the reason why we need to double the width is that higher layer means higher resistance. So we need to double their width to make a lower resistance. And the next step is similar to the last step. We create power stripes on M8 layer, but now we don't need to double their width or their set-to-set distance. And we can see that the power stripe connect to the power rings, and on the M8 layer, it also connects to the power rings. And last, we set the power stripes on M9. So here we also need to double the stripe width and stripe set-to-set distance here. You can see in the left picture, the power stripe width on the M9 layer is 7.2 micrometers, and the one in the M8 layer is 3.6 micrometers. So this is the last floor plan I got, and it just looks like that. And so we complete the floor plan step, and we got the report. This shows that we have no DRC violations, and the total area is 34. It's just for the standard cells of the block, so it's 34,424 micrometers. I think it's just similar to what we got after synthesis. And after floor plating, we move to the last step, is place and route. So the first step of place and route is pre-CTS. In this step, Innovus place standard cells on the layout. So after the pre-CTS step, we can see that these are our standard cells. They are now on the layout. And and also pre-CTS, in this step, Innovus will route some clock wire, just like the picture shows, but it should not. I think it should have not do this, but it really did that. So, but it just routes some clock wire, and it left some clock wire to the CTS step. We can see it later. And the next step is CTS. We can see that the Innovus route all clock wires. So we can see that there are more clock wires here after CTS step. And the last step of place and route is post CTS. And because we already made timing, we can see from the right pictures here, we got all the slacks positive. These are all worst negative slack, so they are all positive, so means that we are mid timing. So this step mainly should not make a big change. We can see it's almost the same as the layout after CTS. And it's the layout with all nets except power and ground is what looks like after post CTS. So the fourth step of place and route is route. In this step, Innovus route all wires, and it also plays feelers. We can see the left picture shows that physical feelers with standard cells, and the right picture just shows standard cells. So there's some difference here, and the density of them is different. And the post route, its function is just pretty similar as the post CTS. It just optimize our layout, and also because we made timing here, and it should not make a big change. So we can see, it's just same as the layout after route. So after place and route, we got the report now. So we take a first look at we take a look at the density and area. We use this command check place ignore feeler in density. Got that we have the layout have 75% density here, which meet the requirement and is larger than what we got after floor plan. I think it's because there are more nets here, maybe. And for the area here, the below area is what we got after SynOpt. So the cell area here is 34,000 micrometers, and we can see what we got after post route is 47,000 micrometers here, because we have some physical cells, feelers here, and subtracting feelers, the areas is also bigger than what we got after sync opt. Okay, I think is because this data after post route is more precise. Yeah. And also we got some physical cells area here, and that's not it's not shows in the report after sync up, because after sync up we didn't have this kind of fillers. So in terms of the setup time, we can see this is the worst path of setup time, and the slack is 0.202, so which means we meet requirement, we meet timing, we meet setup timing at least. And in terms of the hold time, it's also the worst path for the hold time, and the slack is 0.065 is positive, so we meet hold time. In terms of power, we got this two report, and the below report is what we got after post route. The unit of it is microwatt, and the unit after the unit of the report after sync opt is watt. So what we got is that the total power here after post route is much bigger than what we got after sync opt. But the yeah, I think the leakage power is also much bigger than what we got after sync opt. But I think the percentage of the three kinds of power is almost the same. And in terms of frequency, also called performance, the report after place and route told us that okay, we have 7 clock and their period, their rate, and at last we got our DRC report and congestion report. So the report shows that we did not have any DRC here, and the congestion of our design is the max of it is in the post CTS step, but in the route step is 0.44, so it's quite an acceptable range. Yeah, it's in acceptable range. And also it shows that the horizontal direction we have some congestions here, but in the vertical directions we just have little congestions here. So that's all for my transmitter physical design. Thank you for your time.